Welcome to another episode of ZCash Simplified. For everyone who wants to know what this all is about, watch the first intro video about it, about the motivation and everything. So I can now directly dive into the next topic, which is elliptic curves. In the last videos, we did a bit more of the what's the goal of zero knowledge, how to use it in ZCash. And back then it was with some simplified math and or some made up math, so to speak. And today we dive a bit deeper into the real math that we have there that actually is the base of that stuff. For everyone who is not interested in ZCash but only in elliptic curves because of the title, because elliptic curves is also what makes Bitcoin secure until quantum computers. It will be nothing about ZCash today, but only the math behind elliptic curves. With that being said, a quick, as always, agenda and the disclaimer, of course. Agenda, last time we talked about the previous times, talked about the shear transaction and what zero knowledge is, and today we go into the intro of elliptic curves. Today I won't cover the discrete logarithm part of the elliptic curve, which makes it so hard, so really impossible to invert. That will be next time, because I thought maybe it's enough to have the intro. So today I think it's still interesting for everyone who's not that deep into the math, because it's more the idea and the overall intro that you should be able to follow along without any special math knowledge or anything. Next time will be a bit more heavy on that stuff. And as always, a disclaimer, no financial advice. This is just my research, and expect me to be wrong. That being said, let's dive into it. A bit about why do we want that whole thing. We have it in the zero knowledge proofs where we want to prove something without revealing what we are proving. And when we did that for the intuition, I used squaring, so multiplying a number with itself, as the math that cannot be inverted. So in this made up scenario, we said it's impossible to calculate the square root, just to get an intuition. And today we get the first part for something that is actually impossible to invert, and that's elliptic curves. And yes, it's math. Awesome. I hope. For me, it's awesome. Let's talk about it. What do we want? So why do we look for elliptic curves, and what's the overall goal? The overall goal is to have something that we can easily calculate. So it's easy and fast to calculate, but it will be impossible to invert it. And it holds those properties invariance through inputs, so the addition of inputs. So if we do the calculation and we do this calculation of the sum of two numbers, it should be the same output as if we do the calculation independently and then sum it up. If you remember back here with the squaring, we use the multiplication for the calculations, and there, because if you square something, a times b squared is the same as a squared times b squared. So this is the similar intuition here, but this time with addition, which gives us a lot of nice properties later on. So that's a bit the rough idea, and let's jump right into the definition. So yes, now I lost half my my watchers. Elliptic curve definition. An elliptic curve is an algebraic curve. So for you, it's just a curve in the 2D space that's defined by this equation. Actually, you don't need to care about this equation at all. It's just, let's make this a bit bigger. It's just the formal definition, and a and b are constants, and you have x for the x-axis and y for the y-axis. And based on this curve, why use an elliptic curve? Because it has a lot of properties that we see later on that make this usable for us. But overall, let's just say there are properties of the curve, and we will see generally a curve, elliptic curves, depending on A and B, they can look completely different or have different shapes, and we want to look at a curve that has roughly this shape. There is some properties about that, and the definition of what curve you use is depending on the constants A and B, and any encryption, cryptographic stuff defines what A and B to use, and then that's the elliptic curve they use. Bitcoin has a specific elliptic curve with defined A and B, for example, and yeah, every other encryption scheme that uses elliptic curves has this A and B defined, and then the curve is defined. And now we wanted something with addition, right? So let's look at how we can define an addition on a curve. So uppercase, we now always say that's points on the curve. So we have P and Q are points on the curve, P and Q. And we define for every point on the curve, A, we define A dash as the point reflection across the x-axis. So here you already see for R and R dash, so that's just if you reflect it, because this curve is, because of the square here, this curve is completely mirrored, the same across the x-axis, because this is the x-axis, this is the y-axis, and across the x-axis it's completely mirrored. So it's a reflection, so you can always take this point and just put it down by inverting the y coordinate. And now we define for 2 points, P and Q, we take the line, so we have here P and we have Q, doesn't matter, it's completely irrelevant where those points are, it's just for drawing them like that. And now you take those 2 points and draw a line, and now there's one of those properties of an elliptic curve is that if you take 2 points and draw a line through those 2 points, there's exactly one more point where this line crosses the line, the curve. So you have, if you have P and Q and you draw a line, you get this point, then another point, then one more intersection, R dash, and we call it dash because what's interesting for us is the reflected point down here, and we define this point as P plus Q. So we define that we say if we have 2 points and we have this addition P plus Q, the result is R by this process. That's so far kind of good, easy to understand, right? A few special cases, because one, I said there's always a third in the intersection. If you have 2 points and you take the line, there's always a third intersection. But that's not true if you have R and R dash. So that's the only way that you don't have a third intersection. That's the straight line, so the straight line up. And there we define an intersection because mathematicians like to define stuff. We define this third intersection then as a point O at infinity. So this line would go up to infinity, and in some weird way it makes sense for mathematicians to say 2 parallel lines intersect at infinity. So wherever you draw an infinite line, a straight line, here a parallel line parallel to the y-axis, they all, in this definition, intersect at infinity. And this point at infinity is called O, and this is this third intersection then. And another special case, if you have 2 times the same point, like P and P, then you would take the tangent, so the line that is just touching the curve just at this point, and this will cross somewhere at down, very far down, but this curve bends toward the line, so it will have another intersection, but that's the tangent curve on point A. The tangent of the curve on point A is the A plus A way. So with, and every other case you get an obvious third intersection. So that's the addition we have there. Now a bit more to the properties, because today we won't go into the inversion, As I said, today is just about to get a grip on elliptic curve itself. So don't worry, not too bad, but let's get into it. To be able to do some nice math on the stuff, we need this addition to have some properties, because in general, I know this is now a bit the math heavy part, because if you just define a plus q, if you're used to addition in normal numbers, say it this way, it sounds weird, but in the normal numbers, like 1 plus 1 is 2, and you can always say 1 plus 2 is 3 and 2 plus 1 is 3, and so on, because that's the properties that you have with addition. With this point, some of those properties are not that obvious, or you need to at least make sure that they're obvious, so that we have an addition in the system that behaves like we want an addition to behave. And that's what we are doing now. And it's called Abelian Group properties. So to define that we have a set of numbers, so the numbers are our points. The set of things are our points, and we have this definition defined. And now we want to prove 4 properties in that we can make sure that this is an abelian group. So the group is the points, and this O, this infinity point, is the 0 in our group now, in our definition. We define it as 0. And the 4 properties that we need to prove and we need to show are, on the one hand, that it's commutative, I think. A plus B is B plus A. For anyone who just never heard of all those properties, this sounds silly, but if you just define an arbitrary A plus B is something, you cannot always be sure that this is the case. And for us, that's kind of obvious, because if you take the line between A plus B is draw the line between A and B, and you have a certain intersection on the curve. And if you take B plus A, so you draw the line in the other direction, it's an infinite line, so it doesn't matter what's the first and what's the second point, so you get the same one. So A plus B is B plus A. Easy enough. Second thing, in a abelian group, you need a neutral element, so the 0. And this neutral element is, as you guessed it, O. Because if we have the infinity and we have A plus the infinity line, so infinity, we said before, a straight line up gets through the O point. So A plus infinity is lines through that. Next intersection is A dash, reflected back to A. So A plus 0 is A, and we know already A plus B is B plus A, so 0 plus A, or O plus A is also A. Nice. Then every element in this group, except for the 0, every element in this group needs an inverse, so that A plus the inverse is O. And yes, our A dash, the same as before, is the inverse, because again, if you take A and A dash, draw the line, you get to infinity. And infinity has a special case of the O at infinity. If you reflect that, if you reflect infinity, you are back still at infinity. So this A plus A dash is the infinity. Now the only thing that needs a bit more of showing is the associative part, because we want that it doesn't matter in what order we do the addition. So if we first take A plus B, and then to that the result we add C, we want this to be the same as if we first take B plus C and then add A. Now for these points, that's far from obvious, right? Because you have that and you have another point C somewhere. If you take that, you don't know. So let's show it, because math people like to prove stuff. First, let's see where A plus B plus C gets us. We have C here. It's just another arbitrary point. I just drew them in a way that it's kind of easy to see and to follow. Now we have A plus B is D dash reflected is D is the result of A plus B. Now we take D plus C, a line gets us to F dash is F, reflected is F. So this is the result of A plus B plus C. I already drew it here, but don't do it. So A plus B plus C is F, this point. Now we want to show the other way. So we need to take B plus C and then add A to it. And this is a bit more. Now we have C, and now the green one is the other direction. So we take first B plus C. We get the line, so here it's E dash. E dash reflected is E, which is our result of B plus C. Now we have E plus A is the line. And again, we get to F dash. Of course, this is just a drawing. You can prove all of that with the equation for the elliptic curve and everything. You can prove all that mathematically. That it's really always the case, and it's not just because I drew lines here, but this gives you the idea that it's correct. So A plus B plus C is A plus B plus C. So now we have an abelian group, which means we can do all the things that we are used to do with additions. So that all works nicely. And this gives us this nice computation property, which is simply for everyone, just use the normal math, normal number math. It's pretty obvious that we say P plus P plus P plus P, K times, is K times P. But unless we show all those properties, we can't do that, or we would not be able to do it. But now, since we showed that, we can have multiplication of points by scalars. So a simple number, standard, normal number, and we can take the point, and we define that from now on. We write it like that we have a scalar. Scalar is just a number in this case, because P are points. That's not simple numbers, it's points, and K is a scalar. So we have K times B, we write it like that, so that it's clear what's meant. And for that also means for any integer K, we can do, since that is for any integer K, and this also means we can do A times B plus B times B is also A plus B times B. So this gives us this thing that we wanted in the beginning, that we say we have the addition of inputs. And so that's our abelian group properties for elliptic curves. And that's already all there is to the intuition about elliptic curves and how they do. Because it will get a bit more complicated in the next part, but for now, let's say this is all we want to do today, to prove that how to use elliptic curve points, because it's just points on a curve with a defined addition, how to add 2 points. And thanks to the properties of elliptic curves, that means we have an abelian group, which gives us this nice computation property. And that's already it for today. I hope this sparked some interest on how this will be used, because next time you need a lot of interest in a bit of the math. So with that, thanks for watching. See you in the next video.